Do you like books? I mean, really, really like books? Then you're in the right place. Each week, your host, Sam Hankin, interviews the best of today's top-selling authors and the up-and-coming superstars of modern literature. This is The Avid Reader. Here is your host, Sam Hankin.
Hi, everyone. Welcome to another edition of The Avid Reader, brought to you by Wellington Square Bookshop. Our guest today is Forrest Kay, author of Escape from Shadow Physics, The Quest to End the Dark Ages of Quantum Theory, published by Basic Books, released last month. And Adam is a postdoc at MIT. He works with John Bush, the preeminent guy in the field we'll be talking about today, and you'll learn what the letters HQA are all about. So, to me, my hero is, as many of you may know, given the last few interviews, is Richard Feynman, always has been. And he stated, and Adam tells us, I think I can safely say that nobody really understands quantum mechanics. And this is the man who basically invented quantum computing. And Einstein didn't like the idea that his bed was spread like peanut butter all over his room until he opened the door and looked at it, smiling coyly in the corner, all made up with the comforter on top. And, the idea of the Copenhagen thing is that charged particles have no material existence until they're subjected to measurement, which basically means until, well, as Einstein said to Pais as he was strolling along with them, pointing to the moon, saying, so seriously, you're saying if I'm not looking at the moon, it doesn't exist? And like when I was a kid, I thought when I went to bed that my parents dismantled the universe. And then really quickly before I woke up, they put it back together again. And I always wondered, man, this is a lot of work they have to do every night. But it's basically the same thing. And so we'll go into the collapse of the wave function. Obviously, we're going to go into Schrodinger. And then the cool thing about all this is I made an omelet this morning, and I started out putting olive oil in a pan, and I started watching it sizzle, and I thought of Adam. Which you'll find out why. So hi, Adam. Thanks so much for joining us today.
Thank you so much. Good to be here.
So anyway, look, I'm a bookseller, and there's things that I know my listeners and my customers do. They look at the title, and notwithstanding the fact that everyone says you can't judge a book by its cover, they look at the cover, and then they open it up, and then they look at the epigraph, and that's what's happened for the past 15 years at the bookshop. So let's talk about the title. Yeah, the title is interesting because when people look at the title, the first thing they think is, what is this shadow? And what does that mean? Because physics doesn't have shadows. Physics is classical, or it's quantum. Where's the shadow? So, and then the subtitle talks about the dark ages. So are people going to look at this going, huzzah, I'm going to learn all about this stuff? Or this seems like I didn't really know it was all dark.
Yeah. The title is inspired by two separate quotes by two people that I respect a lot. One is Bertrand Russell, and then the other one is Carver Mead. So Bertrand Russell, he was in his study late in his life, and he was contemplating the current physical situation that had been brought about by quantum mechanics. And he was extremely depressed by it because the view had become something akin to idealism, which is a philosophical tradition stating that things that are real are mental things in some sense. And the physical world, if it even existed, was subservient to that. And Bertrand Russell did not subscribe to this. He thought it was very depressing, and he wrote a very depressing note called Modern Physics. And in it, he made reference to the shadow physics of our time. So that's where that inspiration comes from. The second part, the subtitle, comes from a book by Carver Mead, who is an emeritus professor at Caltech. And he wrote a book called Quantum Electrodynamics that starts with the sentence, "I am firmly convinced that the last 70 years will be considered the dark ages of theoretical physics." And I think he wrote that, I don't know, 10, 20 years ago now. So that's where that's where the title comes from. It's kind of drawing inspiration from those two great minds.
I always feel bad for Bertrand Russell because he said like writing Principia Mathematica broke his brain. And then at the end, he realized, oh, I really screwed up. I can't do this because I can't get outside of it. So like, yeah, but and you know, Kurt Gödel basically told him he was wrong. But you know, I'm a layman, so I don't really know what I'm talking about, but that's the way. But yeah, so the epigraph thing, you got the first epigraph, and then you got them like sprinkled throughout, and all of them seem to point to how dumb we are. It's all like, in the future, our descendants are going to turn around and point to us and go, "What? How could they not have known all this?" and like laugh at us. So there's like five of them in there. So why are you so sure that's going to happen?
I feel pretty sure that's going to happen because when you look very closely at the arguments stating that we've moved into a new era of physical understanding where probabilities are the best we can do, they just don't. They're not very compelling, actually. The closer you look, the weirder that statement actually becomes. And part of the reason that there are so many references to the incompleteness of scientific knowledge or history of science getting things wrong, right? Having the wrong idea beginning or the wrong idea being dominant for some time, is that I think that's what's happening today. And I want to show the reader how plausible it is that that could be happening today, because it's happened many times before. So True. Why not today? And then you have to take a look. Is it happening today? And then I think the answer is yes.
Well, it's interesting because, you know, you mentioned so many people that you admire and that even lay people are very familiar with, whether it's Dirac or Schrodinger or Einstein or Feynman or so many others. And, you know, you could say the new guys like you are standing on the shoulders of giants, but you also topple some of the giants over in this book to a certain extent, right?
I mean, I didn't go out to topple anyone, but I think that when you read the thoughts of anyone, no matter how giant they are, you should think about whether they're true or not, right? And it just so happens that I agree with one of the giants and disagree with some of the other ones, you know, right? So the famous debate here is the Bohr-Einstein debate. They were both giants. Heisenberg said that Bohr had a greater influence on the physicists of his generation than anybody else, including Albert Einstein.
Yeah, but that was because he was so cool.
I mean, there's a lot of reasons why. I think it's probably true that he did. Yeah, and in my case, I just very strongly fall on Einstein's side in the debate, even though most people think that Einstein has already been proven wrong and the debate is over.
Yeah, it's funny because, you know, when he said the cosmological constant was his biggest failure, he was wrong because he was right.
You know? Yeah, that's an interesting one.
Okay, so let's sell books. So the idea is like, if you begin at the beginning of your book, and obviously half the people you talk to are going to start with Schrodinger and the cat and blah, blah, blah. But you start with that too, because you're studying and you're in your carrel. And what do you see on the wall?
Sorry, I didn't follow. My carrel? What do you mean?
Well, you know, the carrel is like the little place where you study when you're doing your PhD, where you saw on the wall the graffiti.
Oh, right. You're talking about the very beginning of the book.
Yeah.
So, yeah, I just thought, I don't know why I just came out like this is probably part of the reason I started there is because it's kind of my beginning with quantum physics too. Not that quote, but just that time period, you know. And I didn't understand anything at that period because I was an undergrad. I was in the library, and there was a lot of graffiti all over the walls on on the table all the time. You know, everyone's writing. And one of the things on the wall that I saw was this arrow pointing to nothing. And then it said, Heisenberg may have been here, which is just funny.
Yeah. And that was a good way for you to start. And it's a good way to start the conversation because, again, you know, as lay people, you know, people recognize the phrase, you know, you can know where an electron is, but you can't know how fast it's going, or you can know how fast it's going, but you can't know where it is. That's the basis of quantum theory. So talk a little bit about that, about why it is. And then obviously you're going to lead into the slit experiment and interference, but talk a little bit about that because that really is the groundwork on which you build and tear down.
Yeah. I mean, the Heisenberg uncertainty principle is fundamental to the mathematical machinery of quantum mechanics. And what it says is that there are pairs of variables that have a certain relationship with each other, such that you cannot reduce the uncertainty of one of them without, beyond a certain bound, without increasing the uncertainty of the other one. So one example that people make to try to render this intuitive is taking a photograph of a car. If a car is moving, then there's going to be some level of blur in the photograph. So the photograph won't be perfectly crisp. And the faster it's moving, the more blur that you'll see. Whereas if you get a perfectly crisp photograph of the car, maybe you have an amazing camera, or it's still, but nevertheless, you get a perfectly crisp one and someone tells you it's moving, you can't say anything about how fast it's moving, right? It could be going very fast, could be moving hardly at all or not at all. The fact that you have the absolute pure crispness of it means that you have no information about its velocity in that photograph. So this principle is foundational. It is what led Niels Bohr, among others, to say that the classical principle of causality that had underpinned physics up to the advent of quantum mechanics was now transcended, and that we had no reason to speak of causality in the subatomic world. So that was a very strong position to take at the time. It was taken for a variety of reasons, but the uncertainty principle was really probably the main one. And that great revolution away from strict causality and into probabilities and vagueness is still with us today. It is what I think, I'm not alone, among others, I think that it will eventually be superseded, just like many theories have been superseded in the past. It won't ever become irrelevant. It is self-consistent and perfectly defined for what it is. But one way of maybe seeing my point, or maybe believing it a little bit, is to note that the uncertainty principle is not a new thing that comes out of quantum mechanics. It was already known before quantum mechanics came along. And one of the first examples that Bohr used was from optics and the theory of telescopes. So he would constantly talk about that example to show to kind of illustrate the uncertainty principle in quantum mechanics. And it's the same in audio. The uncertainty principle arises in the theory of sampling audio, or indeed in the theory of sound waves in general, right? It's not strictly a feature of quantum mechanics. It's a feature of a set of mathematical tools. So, yeah.
It's true, but I mean, you know, you can also say perception is reality. If you're listening to a CD, you're listening to ones and zeros, and there's spaces in between that they took out from the analog version of the record. The analog decays, but it's got everything. The digital doesn't decay, but it doesn't have everything. So our perception changes simply because of the medium. Whereas, and also actually, and I jump all around, sorry.
It's all right.
So when you said light, it reminded me of what you talked about at the beginning, which is the idea that the ancients felt like we were emanating these rays that allowed us to see things. And at first I didn't understand why you're even talking about that. But then all of a sudden, intuitively, I kind of did. So maybe you can explain how that works.
So the ancient theory of vision was an interesting amalgam of different ideas. And the dominant theory back in ancient Greece was, well, I don't know how dominant it was. There were two theories. One was that the eyes shot out invisible rays, and those rays kind of flitted over everything. They went in straight lines. They flitted over everything. They melded with the light from like the sun or a fire or lantern or whatever, and then that's what let you see. So it was a theory similar to touch, right? Where like you reach out and touch something. And then that was called extramission, like sending out rays from your eyes. And then there were other people who believed that something came into your eyes. Yeah, so today we know that intromission, things coming into our eyes, is the correct theory. But Plato thought that things went out. Euclid thought that things went out. Ptolemy also thought that. And I started there, I guess, for two reasons. One is it shows one, it's the first example of many in the book of scientific theory getting things wrong, right? You try to think formally about something, it's hard. It's a good chance you're going to get it wrong. But you might have some admixture of truth, which is what happened in that case. And then the other reason is that it is, so far as I know, the very first example in history of the famous particle wave duality, because Euclid believed that the rays shooting out of your eyes were discrete, like little, invisible needles, lots of them shooting everywhere. And then Ptolemy, who also developed this theory, believed that the rays were a continuous kind of flux, right, that came out. And the difference between those two is the difference between discreteness and continuity. It's a particle and a wave. So that's another reason why I started there.
Well, it's interesting because, Ptolemy posited a geocentric solar system universe, and Aristarchus, who got kind of laughed at, he said, no, I think the sun is at the center. And then talk about dark ages, it's not until 1500 that somebody else says that.
Yeah,
exactly. And the thing about it is like, okay, that's a strange one because no one built on what he said. Generally, these guys built on something. It just went away. And it actually is the very dark ages that you're talking about, literally, In
that case, yes. So yeah, that's the most famous example of a scientific revolution of perspective and one theory supplanting another. It's so famous that I hardly even mention it in the book, right?
Yeah.
I mean, it's been written about forever, and there's like nothing that I can add to that. And I think that I'm safe in assuming the reader knows about it, so I kind of draw on it, refer to it, just really briefly. Yeah, but it's true, and it's interesting because the same thing happens in the theory of thermodynamics, because Bernoulli had the right idea about gas molecules and how they behave, and he wrote about it, and he deduced some things the first time he wrote about it in his book. But again, nobody did anything with it. Nobody hardly even paid any attention to it. The dominant theory was very different, and everyone was building on that. So that's what they used.
It's funny. I was sitting looking out the window today, and I have this driveway that's kind of at a really steep angle. Sometimes trucks don't like to come up it. So I ordered this freezer from my daughter's dorm room. And so the guy offloaded it down at the bottom, and then he put it on a hand truck and he wheeled it all the way up. And I was watching him. And I was thinking, okay, basically all we do in life is move mass, and we move mass over time, and you can see mass being moved. So there's a space-time continuum, and there's that guy's world line. I thought, okay, that pretty much explains everything. And I thought, no, that's pretty stupid. But then I thought, well, maybe it really does explain everything. And that's the truth. Why do I need to go to the Planck length? I just saw everything the way it happens. I mean, there's all kinds of stuff going on in the freezer. But I have no idea where I'm going, but that was what happened. That's what happened.
Yeah. It's so funny where the mind goes when you're just, sometimes you have a meditative moment about an everyday occurrence.
I know. I love that.
Yeah.
It's like, enjoying the moment, but you're actually like just watching it and you're in the flow, you're like, it's like when you guys get into the flow and you realize 6 hours has passed and where did it go? And that's another.
Sometimes I have a thought like that where I come back to a place where I've been before, sometimes even after a long time. And I imagine all moments of time compressed into a single moment. And so my younger self is like still there, right? And like there's the continuous being.
Yeah, there's a Transparent Things by Vladimir Nabokov talks about that. I'm looking at his books right this second as I turn. There's the book. And also there's a new movie coming out called, I think it's called Here, with Tom Hanks and the woman from Princess Bride. Forgot her name. But anyway, all it is one room. It's the corner of the room, but it goes from 500 million BC to 2007, and all it is the corner of the room.
Right.
Everything happens there. It looks really cool, and they have that de-aging process they use now. But once again, I'm still not selling your book, so let's go back to it. So actually, the way to go back to it best, because it's like this is the punchline or this is the spoiler, is talking about fluid mechanics and this idea of oil bouncing around somehow explaining quantum theory. So
interesting, huh?
Yeah, well, it's because I'm reading the book and all of a sudden you just say it, and it's like, and then there are really some good pictures in the book too, and great notes as well. But anyway, so what about that?
Yeah, so in 2005 in Paris, these two professors discovered this very beautiful and beguiling fluid dynamic system by accident. They weren't even trying to think about quantum mechanics. But what happens is you can build these in your house for $50. If you have, say, a speaker and then a bath of oil above the speaker, silicone oil, and then you turn on the speaker and you have the bath of oil vibrating just a little bit very quickly, and you take, say, a toothpick or a syringe or something, and you kind of pluck the surface of the oil. It'll pull up a little submillimetric drop, a tiny little drop that lands, but it never coalesces with the surface of the bath because the bath is vibrating. It has so much energy that the air layer between the droplet and the bath never has a chance to fully dissipate before the force of the air on the droplet pushes it back up again. So it just bounces there as long as you want. Then that's cool. And there's a lot of things you can say just about that system. But if you change the frequency a little bit, what winds up happening is first the droplet harmonizes with the bath. When that happens, the whole surface of the bath kind of comes alive with standing waves. So you got this little droplet of oil bouncing really quickly, and then it's surrounded by waves. The waves look like they're just persistent because the droplet and the waves are bouncing in phase with each other. So the droplet is renewing the waves every time it hits, and the waves are kind of just staying there. And at a slightly different regime, when you change the acceleration a little more, it destabilizes, and then the droplet winds up bouncing, not instead of at the very peak of the wave that it created, it comes out just off to the side. And so it's like dropping a ball onto the side of a bowl. It kind of goes off in one direction. And it just so happens that it creates another wave that is just perfect enough to bounce it off, going in the same direction it was before. So the droplet just starts walking over the surface of the bath in a straight line. And those are called walkers, just a different state for the system. Then, well, first of all, when they discovered this, like, this is really interesting. And they started doing all sorts of things. Like, they put multiple ones in together, and they noticed that they would like orbit each other, right? Or they'd walk together like they were dancing and like this kind of wavy motion like this. And then a bunch of them together would bind, they'd enter a bound state similar to crystals, where they would bounce together, bound by their mutual wave field, and they'd be in a stable crystalline arrangement. And then there were different crystals you could make with these things, whether they were all bouncing in phase or out of phase, changed things. So the interesting thing that they noticed, well, they made a conceptual leap very quickly, which would not have been made by everybody. I think that it was very creative and intelligent of them. They realized that it's a droplet and it's a particle and a wave, right? You've got a droplet and the surrounding standing wave, and they're interacting with each other. So maybe this has something to do with quantum mechanics. Maybe it says something about quantum mechanics. So they started doing these experiments to test how close it might be to quantum mechanics, whether they could find any analogies. And they immediately found a whole bunch of analogies. And some of them are very, very, very good analogies. Like the mathematical form of the behavior is roughly identical. So that's pretty interesting. And that forms kind of like I would say, I don't know if it's the backbone, but it's kind of like the core example in the book, where I talk about not all, but maybe half of the analogs that currently exist, maybe less than half actually, and try to explain them. And so, like, look, we have this quantum phenomenon, for example, this thing called quantization. It's where the word quantum comes from. And there's some people who talk about quantization and they wonder what it means. Like, where does it come from? Maybe they have some theory to explain it, but most people don't. Most people don't know where it comes from. But in the hydrodynamic system, it is also quantized in a lot of its behaviors, and it's very straightforward to see where it comes from. So, the idea is very obvious at that point. You just say, well, maybe quantum mechanics has an underlying explanation. Maybe one day we'll figure out a theory that is classical. It has determinism, right? And it generates the statistics that we currently have. It generates them from an underlying non-linear, highly interesting classical theory.
Well, that leads to a lot of thoughts. I mean, especially when you say determinism, because you start out the book saying, basically, you have lots of scientists now saying that every moment we're talking, we split off into another universe. Every possible smallest moment, there's another universe being created. There's no proof for that, and there's no way to empirically begin to prove it. But hydrodynamic quantum analogs, to me, suggest analogy. Analogy suggests that it's not the same thing, but it's very much like this. Or then I start thinking, well, is this just a metaphor? And then I start thinking about Douglas Hofstadter, who basically says everything's a metaphor. Otherwise, we wouldn't be able to do anything, especially communicate. So when you say analog, you're not saying this is quantum mechanics. Are you just saying this is an excellent explanation of how this might actually work?
Right. It's a great question. And I think it's one that is very natural to ask. How good are these fluid toy systems as a guide to the quantum world? Nobody knows. The thing is, the question of analogical thinking in science is a pretty deep question. It's a very old subject, right? And there's been a fair amount written about it. Towards the end of the book, after we've gone through this whole kind of arc of history and we've talked a lot about these analogies and things like that, I raise this question, like, how good are these? Like, how should we think about analogy in science, right? And there's one of the quotes, I actually mentioned it twice in the book, in the beginning and then towards the end, is by this guy, George Polya, who's was a mathematician. And he said that analogy has a share in every discovery, but in some discoveries, it has the lion's share. And that's quite nice, right? The utility, so I don't think anybody is going to argue that analogies are not useful. Sometimes they are extremely useful, right? Like Kepler, for example, used analogies extensively. And they were basically his guiding tools. And he developed his, at the time, extremely original theories about planetary motion using, essentially following analogies. So they can be excellent guides. On the other hand, there's such thing as false analogies. False analogies are easy to come by, and you would be well served to be a little careful about analogies and to explore where they might go wrong and that kind of thing. One thing I think is very important to point out, though, when you're asking this question about analogies, it is that you take the fluid system and you ask yourself, what's going on here? You break it down into a mathematical system, okay? And in the mathematical system, you have kind of like a point particle. You have an ambient wave field. You have the point particle interacting with the wave field by being pushed by the gradient or the slope of the wave, being pushed around. And then when you have more than one particle, you have a complicated wave field being created by multiple particles, but that's basically it. And the other thing you have, which is very important, is oscillation. You have this kind of like vibration of the particle, and it's in harmony, it's in sync with the wave, right? As I explained before. This was the very first interpretation of quantum mechanics before the Copenhagen interpretation. It was developed by Louis de Broglie, who won the Nobel Prize for his postulate, the particle wave duality. Like that was basically kind of his idea. It should apply to everything, not just light. That's what he said. And his idea that he developed in 1924, 1925, 1926, we all built up to this paper in 1927, where he talked about something called the double solution, where you have a particle and it's oscillating and it's in sync with a wave that is surrounding it, and the wave pushes the particle around, and he deduced Schrodinger's equation from that theory. So that the double solution is the quantum version of the droplet experiments that are done in oil on 2D. And that fact is, in my view, highly significant.
Well, in explaining it to me, you're using words like harmony, gradient, you even talk about dancing. And if you express that as a formula, which you can, could you lay that formula on top of another formula that works in the quantum world? Could you lay it on a template?
Well, that's what de Broglie did. That's actually what he did, is he had a non-Newtonian, very original, kind of strange theory that he used to show that if particles exist, and particles behave like this with these, interacting with these waves, then they will, if you follow their tracks over and over, and you do maybe one experiment, say the double slit experiment, over and over again, you will get the statistics that are predicted by the Schrodinger equation. So, he showed in 1927 that this idea can be, if you so desire, intimately connected to quantum mechanics.
What if you use something simpler? Like, I always like when the guy told Arthur Eddington, there's only two people in the world that understand Einstein's theory of relativity, and he goes, who's the other one? But so, which reminds me of the examples you get when you're a kid, like you're sitting in a train, You look next to yourself, you look next, there's a train next to you. And I've done this many times. I feel like I'm moving, the train is stationary, or the train is moving and I'm stationary. I have no idea which one is actually happening. None at all. Is that an analog? It's not. It's a metaphor, right? Is it a metaphor? Or is it an actual explanation of what's happening in terms of my relative position in space and time?
Yeah. So I think that, you might have a hard time finding very clear distinctions between analogy and metaphor unless you can just agree a priori to define them in certain ways, right? So, metaphor differs from simile how, right? Like in simile, you say this thing is like this thing, and in metaphor, you say this thing is this thing when it's not, right? So, they're very, very closely related, and analogies are maybe similes in and in this case, what we're considering is similes in the physical world, right? So you look at one physical system and it is like another's physical system. You don't have to, analogies, you can have analogies all over the place. It doesn't have to be just being in physics. You can use them anywhere you want.
You can only do it certain things though, because I can't say to you, this is like red. There's no way.
Why not?
Because it's not like red.
Yeah, but then it's like a metaphor, right? What are all of the overtones of the concept of red? Like some people associate it with maybe a country, other people associate it with blood or stoplights. And then you can say, my life is just a sea of red right now.
That's a metaphor. No, it's a simile.
It's a simile. My life is red. My life is red right now. Don't talk to me. My life is red.
I will tell you a perfect example is that if you have synesthesia, which I kind of do. Monday's green, Tuesday's brown, Wednesday's dark green, Thursday's dark brown, Friday's orange, Saturday's yellow, and Sunday's white. It's all been that since I've been a little kid.
That's cool.
I know, it is cool. Used to be with numbers too, but I forgot all of those.
Oh, wow. Yeah. Well, I've always been very fascinated with synesthesia. It's really amazing.
Yeah, most of the time I was in an out-of-body experience due to the fact that I was 18 in 1970. So yeah. Plus I forget how to read and stuff. See, this is what I say. I jump around. I really do want to try to sell your book but nothing I'm saying for the most part goes in that direction. So the subtitle, going back to it, you are on a quest for the holy grail of something. So where is, if this is a quest, you gave it the title. So it appears to me you wrote it and you are on a quest to end the dark ages of quantum theory, which is quite the Herculean task. Yeah. So what is your quest? It's like Monty Python.
I think that when I thought that would be a good subtitle, or at least provisionally be a good subtitle, I was referring not necessarily to myself, but to the body of scientists who all agree with me. And there's a fair amount of them, right? It's not just like one or two crazy people, scratching around under some trees or something. It's a lot of fairly distinguished, some of them unknown, some of them very famous, some of them in the academy, some of them not. Just a lot of people who believe that this is the right way to go. And then, ending the dark ages, I already said, Carver Mead, his idea. And it's also, I think, editors and publishers, they like very dramatic titles. So if I had my druthers, I would have maybe picked a quieter title. But, you're trying to please a lot of people at the same time. So
I know. For 10 years, I interviewed people who wrote novels. And then once I started interviewing people who are searching for the seat of human consciousness or stuff you're doing, everybody has a subtitle. You cannot have it without a subtitle.
It's a very nonfiction thing to do. Yeah. I think that nonfiction authors like it because you get to pack more information in there. You get to tell people more stuff.
Yeah, I know. And that's why I'm saying it's important. When this is sitting on the table that has our new science books, people will be drawn to it not only because of the the picture. Who did the cover? Did you do it, or did you vet it, or what?
The cover is a photograph of one of the fluid experiments that was taken in John Bush's lab. It's changed to be kind of shadowy, right? To be like blue and dark tones. The original photograph was done with, it's kind of like a reddish and bluish colors, and that came from the way that they have like light that they shine on the bath, and then there are kind of plastic sheets that create reflections so you can see the distortions in the water more clearly. It's a beautiful photograph. It's on John Bush's webpage. You can see it. And that's where the photo came from.
Well, so if that's the basis for what maybe the Holy Grail is HQA, but so where's HQA going to go now? I mean, you've already told me what it is and how it works, and these guys are dancing, or they're crystalline, or they're doing all these different things, and that's the analog to what happens in quantum theory. But where is it going to go now? You have your initials, you have your theory. Now where?
Yeah, it's a great question. So the current work in HQA is going in 2 different directions. My own work has explored doing these experiments in 3 dimensions. You can't do them physically in 3 dimensions very easily. So I did it in computers. So we're doing kind of some mathematical modeling of 3-dimensional system. And other people are working on other things. There is an attempt to try to make the system be a little bit more like quantum field theory. So there are some papers on hydrodynamic quantum field theory. They're going in that direction. There is work in Paris on time varying media, where you change some features of the bath itself while the experiment is going, and it alters the phenomena of the waves. There's a lot to do, and there's a lot to say about it. The main question is the one we already addressed, the one you asked, which is like, how good of an analogy is this? Is it a red herring? Is this just kind of like barking up the wrong tree? Mix some metaphors, who knows? But I think that the coming years will help answer that question. The HQA researchers are doing this because, first of all, it's very interesting fluid dynamics. Like, forget about quantum mechanics. The system is really beautiful. So weird, it has so many surprising features to it. There's a lot of different things you can say about it, and it's not even close to exhausted. One of the things that someone in the research group said, which I think is right, is that like with this system, it's kind of hard not to get a result. The system is so rich, it's so new, that PhD students regularly just get novel results that are worth a paper.
That's like, it reminds me of Einstein again, because of Brownian motion, which is part of the reason he got the Nobel Prize. Because that's really cool too, It shouldn't be there. It shouldn't be stuck in classical when it's not classical. And yours is classical physics explaining something that's exactly the opposite of it.
Yeah, that's the promise. And it doesn't explain quantum physics. It's an analogy, but it's classical. It's purely deterministic, fluid mechanics. The equations are known, and that's fascinating. That's very suggestive.
Huh. When you said red herring, that was a better example of the red thing.
There you go.
Well, okay. So, I know what I wanted to ask you, because I was listening to another interview when you were talking about your 2 PhDs, the first in comparative literature, and he was trying to ask if the 2 of them intersected in any way. And I was thinking about it, because like reading Borges, for example, it's almost like another analog, the Library of Babel or something like that. I mean, were there books and authors that pushed you into this other place? There must have been.
That kind of led me to this.
Yeah.
Are you asking to say? Yeah. That's a long story, like how I wound up in this world. Yeah. It's it's a weird mixture. It's a weird mixture of my own interests, research interests, and intuitions, and reading around the subject. So,
What does that mean, reading around it?
Just constantly reading about it, the things that are tangentially related to it, following the trail of breadcrumbs from one reference to another, that kind of thing. Yeah, so there have been a lot of very useful books, but I think that one turning point was when I first saw the hydrodynamic fluid system.
Really?
Yeah, because when I first saw it, I think it was in a Wired article.
Wow.
And in 2014, it was about 10 years ago, and it was relatively new. It was about 9 years old, and I saw it, and it was just so visually striking, and it was also so consonant with some of the things that I had been thinking myself, that I just kind of got fascinated by it. But that wasn't a book, right? It was like an article, and the reason the article really kind of landed was because of the images. And that's I think pretty cool. Is you can read about something a lot. The images are very convincing to a certain type of person.
Well, that's how I felt, because you were explaining it, and then I turned the page and there's those two images at the top, and I go, oh, that's what you do. You go, oh.
Yeah.
Hey, so when did you start thinking about this stuff? Like when you were a kid, did you do like I did and I still do, like wake up in the morning and you go, what the hell is this? Did you ever do that? Like, what
the hell is this?
Yeah, what is this? What is,
Yeah. I mean, so when you say this stuff, do you mean quantum mechanics, or do you mean?
No. You wake up in the morning and you're inside of something and you go, what's going on? What is this? You just like, you wake up and you question things immediately. I mean, it seems like you did. It seems like when you were a kid, you must have done this kind of stuff. You must have thought, I need to know something. I need to know.
Yeah. So I think that for me, I was always interested in science when I was younger. And I remember when I was in 5th grade, I wanted to learn about the theory of relativity. And I asked this woman who had a kind of post-school care program for kids. They would go there after school because their parents couldn't pick them up at pickup time. I asked her about, hey, what's the theory of relativity? And she told me that everything is relative. Like an apple is only relative in relation to an orange, right? And I was really disappointed because that is not what I wanted to learn about. So I definitely had that instinct, like I wanted to know things, like big things. But in terms of really starting to think hard about reality, like what is this thing? Happened probably towards the end of undergrad. That's probably when I woke up. Prior to that, I was interested in hanging out with my friends. I was interested in playing games or having fun. Actually, that's not even true, because I'm realizing now that it just had a different form, right? Because when I was in high school, I was very interested in religious philosophy. I was very interested in like Hinduism and Buddhism, right? And for the same reasons as I was asking, the teacher that thing in 5th grade. So honestly, I think that probably a lot of people have this experience. There's not really any moment where I woke up and I was like, oh, it took different forms at different stages of my life.
Now we're in a kind of a therapy session.
Huh.
So, what? I think this is better at selling books than anything, is the idea of people listening to what you just said and getting to know you. I mean, the book, we've talked about it and they understand that they're excited about it. But the idea of learning about the author from a different viewpoint, like we just did now, I think that's a great way to end it, because I think that was really nice what you said.
Sweet.
And
I appreciate that.
okay, well, thanks so much, Adam. It was a pleasure talking to you.
Yeah,
Sorry.
it was good.
Thanks for putting up with me.
Oh, it was a joy. And thanks for putting up. I feel like I'm in a noisy environment. I don't know if you could hear some of that, but yeah,
No,
it was
actually,
good.
the little bit of noise there is, my engineer is really good at cleaning it up.
Cool.
So that'll work. So again, thanks again.
Yeah, it was a pleasure. Have a great rest of your day. Thank you.
You too. Bye-bye.